The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, so we'll get started. And as I mentioned, to some degree, this is going to be review and setting our notation and conventions clear. So our first topic is the Schrodinger equation. So this Schrodinger equation is an equation that takes the following form. IH bar, partial derivative of this object called the wave function, that depends on x and t, is equal to minus h squared over 2m, second derivative with respect to x, plus v of x and t, psi of x and t. And that's a full equation. That's Schrodinger equation. Now, actually, this is not the Schrodinger equation in most generality, but it's a Schrodinger equation for the case that you have a potential that depends on x and time. For the case that you're doing non-relativistic physics, because this thing, you may remember, is p squared over 2m is the kinetic energy operator. So p squared over 2m is non-relativistic. That's a non-relativistic kinetic energy. So this is non-relativistic. Moreover, we have just one x here. That means it's a particle in one dimension. So we've done a few things, but this is general enough to illustrate our ideas. And the most important thing that should be said at this point is that psi of x and t, which is the wave function, belongs to the complex numbers. It's a complex number, and that's by necessity. If psi would be real, this quantity, the right-hand side, would be real. The potential is a real number. And the left-hand side, on the other hand, if psi is real, its derivative would be real, and this would be imaginary. So it's just impossible to get a solution of this equation if psi is real. So psi complex is really the fundamental thing that can be said about this wave function. Now, you've used complex numbers in physics all the time. And even in electromagnetism, you use complex numbers, but you use them really in an auxiliary way only. You didn't use them in an absolutely necessary way. So for example, in E&M, you had an electric field, for example, for a circularly polarized wave. And you would write it as this. Let me put a z here. E0. X hat plus y hat, those are unit vectors. I is a complex number, is the square root of -1, e to the I k z minus omega t. You typically wrote things like that, but in fact, you always meant real part. An electric field is a real quantity. And the Maxwell's equations are real equations. This is a circularly polarized wave, and this whole thing, by the time you take the real part of this, all these complex numbers play absolutely no role. It's just a neat way of writing a complicated electric field in which the x component and the y component are out of phase, and that you have a wave at the same time propagating in the z direction. So this, in here, E is real, and all i's are auxiliary. This is completely different from the case of the Schrodinger equation. This I there is fundamental. The psi is the dynamical variable, and it has to be complex. So we make a few remarks about this Schrodinger equation to get started. First remark is that it's a first order differential equation in time. This has implications. There's two derivatives, or maybe for some funny Hamiltonians you could have even more than two derivatives or more complicated things, but definitely there's just one derivative in time. So what this means is that if you know the wave function all over space, you can calculate what it's going to be a little time later. Because if you know it all over space, you can calculate this right-hand side and know what is the time derivative. And with the time derivative, you can figure it out what it's going to be later. A first-order differential equation in time is something that if you know the quantity at one time, the differential equation tells you what it's going to be later. So that's really sufficient psi of x, of all x's, at some time t naught determines psi at all times. Second property, fundamental property, the equation is linear. So if you have two solutions, you can form a third by superposing them, and you can superimpose them with complex coefficients. So if you have two solutions, psi1 and psi2, then A1 psi1 plus A2 psi2 is a solution. And here the A's belong to the complex numbers. So there, A1 and A2 are complex numbers. As far as complex numbers are concerned, the first thing you just need to know is definition of the length of a complex number. So if you have z, a typical name people use for a complex number, having two components, a plus ib, where a and b are real, there is the definition of the complex conjugate, which is a minus ib. And there's the definition of the length of the complex number, which is square root of a squared plus b squared, which is the square root of z times z star. So that's for you complex numbers. So the property that makes this into a physical theory and goes beyond math is what you know is the interpretation of the wave function as a probability. So what do we construct? We construct a p of x and t, or sometimes called the rho of x and t as a density, and it's defined as psi star of xt. Now, here the notation means this psi star, we put the star here. It really means psi of x and t complex conjugated. You complex conjugate the wave function, and you get that. We put the star here and typically don't put the parentheses unless you have to complex conjugate something that is a little ambiguous. So psi star of x and t times psi of x and t. And this is called the probability density. Probability density. And the interpretation is that if you take p of x and t and multiply by a little dx, this is the probability to find the particle in the interval val x comma x plus dx at time t. So this is our probability density. It's a way to make physics out of the wave function. It's a postulate. And the consequence of this postulate, since we're describing just one particle, is that we must have that the particle is somewhere. So if we add the probabilities, that the particle is somewhere all over space, this is the probability that the particle is in this little dx. We integrated, that must be equal to 1. And this must hold for all times. In terms of things to notice here, maybe one thing you can notice is the units of psi. The units of psi must be 1 over square root of length, because when we square it and we multiply by length, we get 1, which has no units. Key property of the Schrodinger equation. We will revisit the Schrodinger equation later and derive it sort of the way Dirac derives it in his textbook, as just a consequence of unitary time evolution. It will be a very neat derivation. It will give you a feeling that you really understood something deep about quantum mechanics. And it will be true, that feeling. But here, we're going to go the other way around, just simply ask the question. Suppose you have a wave function such that the integral of this quantity at some specific time is equal to 1. Will this integral be equal to 1 for all times, given that it is 1 at some given time? Now, you'll say, well, why do you ask that? I ask that because actually this could be a problem. We've said that if you know the wave function all over space at one time, it's determined everywhere. So any time later. Therefore, if I know the wave function at time equals 0 is good, time equal t0 is a good wave function, am I guaranteed that when I solve the Schrodinger equation, the wave function will be normalized well later? Yes, you are. And it's a simple or interesting exercise that we'll call it a quick calculation that I'll leave it for you to do. Which is show that ddt of this integral psi of x and t squared dx is equal to 0. So basically what this is saying, you got here 1, but think of this integral. I'm sorry, I'm missing a dx here. Think of this integral for all times. Now it could be a function of time, because you put an arbitrary time here. The integral might depend on time. So it's a good question to think of that integral as that may be a function of time and takes its derivative. If its derivative is 0 for all times, and at some time is equal to 1, it will be 1 forever. So you must show that this is true. Now this, I think you've done one way or another, several ways maybe in 804. But I ask you to do it again. So this is left for you as a way to warm up on the subject. And you will see actually that it's a little subtle. It's a little delicate because how is it going to go? You're going to go in and take the derivative of psi star. You're going to take the derivative of psi and you're going to use the Schrodinger equation. You're going to take the derivative of psi star and you're going to use the complex conjugate of the Schrodinger equation. It's going to be a little messy, but then you're going to do integration by parts and you're going to get 0, but only if you throw away the terms at infinity. And what gives you the right to throw them away? You will have to think. And the answer is that you will throw them away if the wave function goes to 0 at infinity, which must do it. The wave function must go to 0 at infinity, because if it didn't go to 0 at infinity, it went to a constant at infinity, it would pick up an unnormalizable thing here. So the wave function definitely has to go to 0 at infinity. But that will also not be quite enough if you're careful about what you're doing. You will have to demand that the derivative of the wave function doesn't blow up. It's not asking too much, but it's asking something. A function could go to 0, presumably, and its derivative at the same time blow up, but it would be a very pathological function. This will bring us to something that we said we're going to try to be precise, but it's not so easy to be precise. When you try to be precise, you can exaggerate and go precise to a point that you're paralyzed with fear with every equation. We don't want to get that far. We want you to notice what happens and just look at it and state what you need. Why can't we be precise? Because at the end of the day, this equation is extraordinarily complicated and maybe crazy if the potential is crazy enough. So functions, mathematicians can invent crazy functions. Things like a function that is 1 for every rational number and 0 for every irrational number. Put that for a potential here, and who knows what one gets. So we're going to take mild functions. We're not going to make them very complicated, and we're going to be stating very soon what we need. So what you need for this to work is that the function goes to 0 and the derivative goes to 0. Yes?
The potential has to be real always?
The potential is real at this moment, yes. For the discussion that we're doing here, V is also a real number.
Can it be complex?
Sorry?
Can it be complex?
It could be in certain applications for particles in electromagnetic fields. You can have something that looks like a complex Hamiltonian. So we will not discuss that in this couple of lectures, but maybe later.
Okay.
Yes?
Are there any conditions that the potential has to be time independent?
Well, at this moment, I put it time dependent. Those are complicated potentials, but they're sometimes necessary. And we will discuss some of them. We will have very simple time dependencies. Otherwise, it's difficult to solve this equation. But very soon, in about 5 minutes, I will say, let's consider time-independent things to review the things that are a little more basic and important that you should definitely remember well. OK, so that's this part of the Schrodinger equation. I want to remind you of another concept called the current, probability current. Probability current. What is it? It's a j of x and t that, as you will review in the homework, is given by h over m, the imaginary part of psi star d psi dx. So it's a real quantity, and It's called the probability current, and it goes together with this probability density. This probability density that we wrote over here. So it's the current associated to that density. Let's think a second what this means. In electromagnetism, you have currents and charge density. So in E&M, you have a current that is a vector and a charge density. Now, this current could also be a vector if you're working in more than one dimension. It would be a vector. But if you have electromagnetism, the most famous thing associated to electromagnetism currents and charge densities is the so-called conservation law. This differential equation satisfied by the current and the density. Divergence of J plus d rho dt is equal to 0. That means charge conservation. You may or may not remember that. If you don't, it's a good time to review it in E&M and check on that, discuss it in recitation, think about it. This means charge conservation as we usually understand it. And the way to do it, I'm saying just in words, is you think of a volume, you consider how much charge is inside, and you see that the rate of change of the charge is proportional to the current that is escaping the volume, which is to say charge is never destroyed or created. It can escape a volume because the charges are moving, but if it doesn't escape, well, the charge remains the same. So this is charge conservation, and this is the same thing. So the divergence of J in this case reduces to dJ dx plus d rho dt equals 0. It has a very similar interpretation. So perhaps in equations, it's easier to think of the interpretation. Consider the real line and a point A and B with A less than B, and define the probability PAB of t of finding the particle in this interval between A and B at any time. You should be able to show, and it's again another thing to review, this you can review, and this review as well. You will use this differential equation and things like that to show that dPAB dt, the rate at which the probability that you find the particle in this interval changes depends on what the current is doing here and what the current is doing here. So it's actually given by J of A and T minus J of B at time t. You can show. And please try to show it. So what does that mean? You can have the particle here at any time, but if you want to know how that probability is changing, you must see how it's leaking from A or how it's leaking from B. Now, J's are defined by convention positive to the right. So if there's a current, a bit of current at A, it increases the probability. This particle is sort of moving into the interval. And here at B, if there's a positive current, it decreases the probability. So finally, for wave functions, the last thing we say is that these wave functions you want them normalized, but we can work with them, and they're physically equivalent if they differ just by a constant. So a psi1 and a psi2 are said to be equivalent if psi1 of x and t is equal to some complex constant times psi2 of x and t. Now you would say, well, I don't like that. I like normalized wave functions, and you could have a point there. But even if these are normalized, the two wave functions could differ by a phase. And they would still be physically equivalent. This is part of the definition of the theory. The definition of the theory is that these wave functions are really physically equivalent and indistinguishable. And that puts a constraint on the way we define observables. Any observable should have this property, that whether we use this wave function or the other, they are give you the same observables. So if your wave functions are normalized, this can be a complex constant of length 1. Then one normalized implies the other is normalized. If they're not normalized, you can say, look, the only reason I'm not normalizing it because I don't gain all that much by normalizing it. In fact, I can do almost everything without normalizing the wave function, so why should I bother? And we'll explain that also as well very soon. So this is something that is part of the physical interpretation, and we should keep it. So now we've reviewed the Schrodinger equation. Next thing we want to say is the most important solutions of the Schrodinger equations are those energy eigenstates, stationary states, and let's just go through that subject and explain what it was. So I'm going to start erasing here. And so we're going to look at stationary solutions. Now, I've used this wave function with a capital psi, solutions, for a purpose, because I want to distinguish it from another psi that we're going to encounter very soon. So stationary solutions, and we'll take it from now, assume V is time independent. The case is sufficiently important that we may as well do it. So in this case, the Schrodinger equation is written as IH bar d psi dt, and we write it with something called an h hat acting on psi, and h hat at this point is nothing else than minus h squared over 2m second derivative with respect to x plus v of x. We say that h hat is an operator acting on the wave function psi on the right. Operator acting on that. What does that mean? Basically, when we say an operator acts on some space, we mean that it takes elements of that space and moves them around in the space. So you got a wave function which is a complex number that depends on x and t ultimately, and then you act with this thing, which involves taking derivatives, multiplying by v of x, and you still got some complex function of x and t. So this is called the Hamiltonian operator, and it's written like that. This Hamiltonian operator is time independent. So what is a stationary state? A stationary state of, so the way it's defined is as follows. A stationary state, of energy E, which is a real number, is a psi of x and t of the following form. it's a simple form. It's a pure exponential in time times a function that just depends on x. So it's a pretty simple object. So what is it? We say that this is a stationary state, e to the minus I et over h bar psi of x. And this psi is in purpose different from this psi, doesn't have the bar at the bottom, and that signals to you that that's the time-independent one. So this also belongs to the complex numbers, but doesn't depend on time. So it's called stationary because, as it turns out, when we will compute expectation values of any observable on this state, in this stationary state, it will be time independent. In particular, you know one thing that is observable is the probability density. And when you look at that, look at this, you have psi star times psi. Since E is real, this phase cancels. This is really a phase because E is real. Therefore, psi star psi, the E cancels, and all the time dependence cancels and goes away. Same thing here for the J. The x derivative over here doesn't do anything to that phase. Therefore, the phase e to the I et over h bar cancels from there too, and the current also has no time dependence. So this will be the case for any operator that is called a time-independent operator. It will have time-independent expectation values. So you can ask anything about some familiar operator, energy operator, momentum operator, angular momentum operator, all the famous operators of quantum mechanics, and it will have real expectation values. So, as you know, you're supposed to now plug this into this equation, and it's a famous result, and let's just do it. Plug back into the top equation, so we have I h bar. The ddt will only act on the phase because the psi has no time dependence. And on the other hand, on the right-hand side, the h has nothing to do with time. And therefore, it can slide through the exponential until it hits psi. So here you have h, well, I'll put the exponential in front, h on little psi. So we multiply here, and what do we get? Well, the h bars cancel, the I and minus I gives you 1, you get an e in front, so you get e times this phase, psi of x, and the phase is supposed to be here, but I cancel it with this phase as well, and I get on the right-hand side h psi, that I will put it as a left-hand side, and this is the time-independent Schrodinger equation. So far, this is really a simple matter. We've written a solution that will represent a stationary state, but then this energy should be such that you can solve this equation. And as you've learned before, it's sometimes not so easy to solve that equation. So what do we want to say about this equation? Well, we have a lot to say, and a few things will be pointed out now that are very important. So we have a differential equation now. This differential equation has second derivatives with respect to x. Now it has no time derivatives. The time has been factored out. Time is not a problem anymore. This equation, in fact, looks quite real. in that it seems that psi could even be real here. And in fact, yes, there's no problem with this psi being real. The total psi just can't be real in general. And, but this one can be real, and we'll consider those cases as well. So things that we want to say is that this is a second-order differential equation in space. So second-order differential equation in space. You could write it here. The H operator has partial derivatives, but this time, you know, might as well say that this is minus h squared over 2m, the second psi dx squared plus v of x times psi of x. Because psi only depends on x, so might as well write it as complete derivative. So second order differential equation. And therefore, the strategy for these equations is a little alternate to the Schrodinger equation. We said in the Schrodinger equation, if we know the wave function everywhere, you know it later. Here, if you know it at one point, the wave function, and you know the derivative at that one point, you have it everywhere. Why is that? Because that's how you solve a differential equation. If you know the wave function and the derivative at the point, you go to the equation and say, I know the wave function, then, and I know the first derivative, then I know the second derivative. So a little later, I can know what the first derivative is. And if I know what the first derivative is a little later, I can then know what the wave function is a little later, and you just integrate it numerically. So you just need to know the wave function psi of x0 and psi prime at x0 suffice for a solution. When v is regular. That is, if v is not too complicated or too strange, because you know you can always find exceptions. You have the square well potential, and you say, oh, I know the wave function is 0 here, and its derivative is 0. Does that determine the solution? No, because it's infinite. There's no space here, really, and you should work here. So basically, unless v is really pathological, psi and psi prime are enough to solve for everything. And that actually means something very important, that if psi is equal to 0, at x0 is equal to 0, and psi prime at x0 is equal to 0, then under these regular conditions, psi of all x is 0. Because you have a differential equation in which the initial value is 0, the psi prime is 0, and you go through the equation, you see that every solution has to be 0. It's the only possibility here. So what happens now is the following, that you have a physical understanding that your wave function, when it becomes 0, it may do it slowly, that it's becoming 0, but never quite being 0. But if it's 0, it does it with psi prime different from 0, so that the wave function is not 0 all over. So this is a pretty important fact that is useful many times when you try to understand the nature of solutions. So what else do we have here? Well, we have energy eigenstates and the spectrum. So what is an energy eigenstate? Well, it's a solution of this equation. So a solution psi, a solution for psi is an energy eigenstate. Then the set of values of E is the spectrum. And if two values of E correspond, if there is a value of E that has more than one solution, we say the spectrum is degenerate. So a degenerate spectrum is more than one psi for a given E. So these are just definitions, but they're used all the time. So our energy eigenstates are the solutions of this. The funny thing about this equation is that sometimes the requirement that psi be normalized means that you cannot always find a solution for any value of E. So only specific values of E's are allowed. You know that for the harmonic oscillator, for example. And therefore, there's something called the spectrum, which is the allowed values. And many times you have degeneracies, and that makes for very interesting physics. So let's say a couple more things about the nature of this wave function. So what kind of potentials do we allow? We will allow potentials that can fail to be bounded. What do we allow? We allow failure of continuity. Certainly, we must allow that in our potentials that we consider, because you have even the finite square well. The potential is not continuous. You can allow as well failure to be bounded. So what is a typical example? The harmonic oscillator, the x squared potential, is not bounded. It goes to infinity. So we can fail to be continuous, but we can fail at one point, another point, but we shouldn't fail at infinitely many points, presumably. So it's piecewise continuous. We can fail to be bounded, and it can include delta functions, which is pretty interesting, because a lot of physics with these delta functions, but a delta function is a complicated thing. We'll include delta functions, but not derivatives of them, nor powers. So we won't take anything more strange than delta functions, collections of delta functions. So this is really how delicate your potentials will be. They will not be more complicated than that, but for that, we will assume, and it will be completely consistent to require the following for the wave function. So psi is continuous, psi of x is continuous and bounded, and its derivative is bounded. Psi prime is bounded.
What about the behavior at infinity?
Sorry?
What kind of extra conditions do we have to impose of size behavior at infinity?
Well, I will not impose any condition that is further than that, except the condition that it be normalizable. So, and even that we will be a little, how would I say, not too demanding on that, because there will be wave functions like momentum eigenstates that can't be normalized. So we'll leave it at that. I think probably this is what you should really box, because for a momentum eigenstate, e to the I px over h bar. This is a momentum eigenstate. This is continuous. It's bounded. The derivative is bounded. It's not normalizable, but it's so useful that we must include it in the list of things that we allow. So bound states and non-bound states are things that are not normalizable. So I don't put normalization. Now, if you put normalization, then the wave function will go to 0 at infinity. And that's all you would want to impose, nothing else. So really, in some sense, this is it. You don't want more than that. Sorry?
Is normalization sufficient to ensure that?
Not that I know. I don't think so.
Why is integration by parts generically valid?
It is probably valid for restricted kinds of potentials. So you could not prove it in general. So, you know, there may be things that one can generalize and be a little more general, but I'm trying to be conservative. I know that for any decent potential, and we definitely need psi prime bounded, and wave functions that go to 0, the only ones I know, they also have psi prime going to 0, but I don't think it's easy to prove that's generic unless you make more assumptions. So, all right, so this we'll have for our wave functions. And now I want to say a couple of things about properties of the eigenstates. Now, we will calculate many of these eigenstates, but we need to understand some of the basic properties that they have. And there's really two types of identities that I want you to be very aware that they play some sort of dual role, and an interesting dual role, and has to do with this wave function. So the eigenstates of H hat, these are the energy eigenstates. You can consider them and have them make a list of them. So you have an energy E0 less than or equal to E1, E2 just goes like that, and you have a psi 0, psi 1, all these wave functions, and then H hat psi n is equal to En psi n. You have a set of solutions. So this is what will happen if you have a good problem. A reasonable potential and nothing terribly strange going on. There will be a lot of solutions, and they can be chosen to be orthonormal. Now, at first sight, it's a funny term to use, orthonormal. This is a term that we use for vectors. Two vectors are orthogonal, and we say they're orthonormal if they have unit length and this like that. But what do we mean that two functions are orthonormal? Well, are functions vectors? Well, that's a little dubious, but the way we will think in quantum mechanics is that in some sense, functions are vectors in an infinite dimensional space. So it's just vectors, but not in 3 dimensions. Why? Think of it. If you have a function, you have to give values, independent values at many points, infinitely many. And if you give all those values, you got the function. If you have a vector, you have to give components, and you got the vector. So in a sense, to give a function, I have to give a lot of numbers, and I can say the first vector is the value along the direction. The first component is the value around 0. The second unit vector is the value about 0.01, 0.02, go on. And then list all of them, and you have a vector of infinite dimensions. You'll say, totally useless. No, it's not totally useless. It's actually, if you visualize that, and we'll do it later more, you will be able to understand many formulas as natural extensions. So what does it mean that these two functions are orthonormal? Well, a dot product or an orthonormality is to say that the dot product is 0. And the way we dot product two functions, psi m and psi n of x, is we take their values at the same point, we star 1, and we integrate. And if this is equal to delta mn, we say the functions are orthonormal. So, normal. So, ortho for orthogonal, which says that if m is different from n, the Kronecker delta, that symbol that is equal to 1 if the two labels are the same or 0 otherwise, if they're different, you get 0. The inner product, this left-hand side is called the inner product, is 0. On the other hand, if they are the same, if m is equal to n, it says that the integral of psi squared is 1, kind of like a wave function that is well normalized. So we say normal for orthonormal. So these are orthonormal wave functions, and that's good. This is called orthonormality. But then there's a more subtle property, which is that this set of functions is enough to expand any function in this interval that you're doing your quantum mechanics. So if you have any reasonable function, can be written as a superposition of these ones. So this differential equation furnishes for you a collection of functions that are very useful. So this is orthonormality. There's also completeness, which is to say that any function can be written as a sum of this function. So I will write it as it is. Psi of x, an arbitrary psi of x, can be written as Bn psi n of x, n equals 0 to infinity, where the Bn's are complex. So this is an assumption, but it's very solid assumption. When you study differential equations of this type, Sturm-Liouville problem, this is one thing that mathematicians prove for you, and it's not all that easy. But the collection of wave functions is good in this sense. It provides you a complete set of things that any function can be written in terms of that. I'm not saying this satisfies any particular equation. You see, this function satisfies very peculiar equations. There are those equations, but this is an arbitrary function. And it can be written as a sum of this. Since these equations have different energies for different psi's, this psi here satisfies no obvious equation. But here is the problem that this is useful for. Suppose you're given a wave function that at a given time, you know what it looks like. So here is your wave function, psi, and you know that psi at x and time equals 0 happens to be equal to this psi of x that we wrote above. So it's equal to Bn psi n of x. Well, if you know that, if you can calculate these coefficients, that is, you have the wave function at time equals 0 is known, say, and it's given by this thing, which is then written in this form. If you can write it in this form, you've solved the problem of time evolution, because then psi of x at any time is just simply obtained by evolving each component, which is Bn e to the minus I E n t over h bar psi n of x. So this is the important result. Now, look what has happened. We replaced each term, we added this exponential. Why? because then each one of this is a solution of the full Schrodinger equation. And therefore, a superposition with complex coefficients is still a solution of the Schrodinger equation. Therefore, this thing, I've put by hand this, you would say it's ad hoc. No, it's not. We've put it by hand, yes, but we've produced a solution of the Schrodinger equation, which has another virtue. When t is equal to 0, it becomes what you know the wave function is. So since this solves the Schrodinger equation, and at time equals 0 gives you the right answer, and you remember that the Schrodinger equation, if you know it at time equals 0, determines the wave function everywhere, this is the solution. It's not just a solution, it's the solution. So you've solved this equation, and it's a very nice thing. It all depends, of course, on having found the coefficients Bn. Because typically, at time equals 0, you may know what the wave function is, but you may not know how to write it in terms of these coefficients Bn. So what do you do then? If you don't know those coefficients, you can calculate them. How do you calculate them? Well, you use the orthonormality. So you actually take this and integrate against another psi star. So you take a psi star sub m and integrate, multiply and integrate. And then the right-hand side will get a Kronecker delta that will pick out one term. So I'm just saying in words a two-line calculation that you should do if you don't see this as obvious, because it's a kind of calculation that you do a few times in life, then it becomes obvious and you never do it again. And it's minus infinity to infinity dx psi m star of x psi of x dx. So Bm is given by this quantity, or Bn is given by this quantity. You obtain it from here plus orthonormality. So once you have this Bn, you can do something that may, you look at these things and you say, well, I'm bored, what should I do? You say, well, you have Bn, plug it back. What happens then? And you say, why would I plug it back? I don't need to plug it back, and that's true, but it's not a crazy thing to do, because it somehow must lead to some identity, because you solve an equation and then plug it back and try to see if somehow it makes sense. So either it makes sense or you learn something new. So we were supposed to calculate the Bn's, and now we have them, so I can plug this back here. So what do I get? Psi of x now is equal to the sum from n equals 0 to infinity, Bn, but this Bn is the integral of psi n star of x prime. I put here psi of x prime, dx prime. I don't want to confuse the x's with x prime, so I should put x primes all over here. Psi n of x. Well, can I do the integral? No. So have I gained anything? Well, you've gained something if you sort of write it in a way that psi is equal to something times psi. That doesn't look all that simple, but we can at least organize it. Let's assume things are convergent enough that you can change orders of sums and integrals. That's an assumption we always do. I'll write like this, the dx prime, and now I'll put the sum here, equals 0 to infinity of psi n star of x prime, and I'll put the other psi here as well, the psi n of x over here. I'll put a parenthesis, and finally the psi of x prime here. So now it's put in a nice way. And it's a nice way because it allows you to learn something new and interesting about this. And what is that? That this must be very peculiar function, such that integrated against psi gives you psi. And what could it be? This is of the form, if you wish, dx prime, some function of x and x prime, times psi of x prime. So this k is this thing. Well, you can try to think what this is. If you put a delta function here, which may be a little bit of a cheat, you will figure out the right answer. This must be a function that sort of picks out the value of the function at x by integrating. So it only cares about the value at x. So it must be a delta function. So in fact, this is a delta function, or should be a delta function. And therefore, the claim is that we now have a very curious identity that looks as follows. It looks like n equals 0 to infinity, psi n star of x prime, psi n of x is actually delta of x minus x prime. So this must be true. If what we said at the beginning is true, that you can expand any function in terms of the eigenfunctions, then, that's not such a trivial assumption, and therefore it allows you to prove something fairly surprising. That this must be true, that this identity must be true. And I want you to realize and compare and contrast with this identity here. One is completeness, one is orthonormality. There are two kinds of sums going on here. Here you sum over space, and you keep labels arbitrary, label indices here arbitrary. So you sum over space. These functions depend on space and on labels. You sum over space and keep the labels, and you get sort of a unit matrix in this space, in the space of labels. Here, you keep the positions arbitrary, but sum over labels. And now you get like a unit matrix in the space of positions. Something is 1, but actually infinite, but you could do better when x is equal to x prime. So if you think of it as a matrix, this function in x and x prime, it's a very strange matrix with two indices, x and x prime. And when x is different from x prime is 0, but when x is equal to x prime is 1, but it has to be a delta function because continuous variable. But it's the same idea. So actually, if you think of these two things, x and m, as dual variables, this is a matrix variable, and then you're sort of keeping these two indices open and summing over the other index, multiplying in one way, you get a unit matrix. Here, you do the other way around. You have a matrix in m and n, and this is a more familiar matrix, but then you sum over the other things. So very dual, and two properties that look very different in the way you express them in words. One is that they're orthonormal. The other is that they're complete. And then suddenly the mathematics tells you that there's a nice duality between them. So last thing I want to say today is about expectation values, which is another concept we have to review and recall. And so let's give those ideas. So if we have a time-dependent operator, we'll do time-independent operators, I'm sorry. time independent operator. And this operator will be called a hat. No time dependence on the operator. So then we have the expectation value of this operator on a normalized state. So what does that mean? The expectation value of this operator on a state, on a wave function here. Now this wave function is time dependent. So this expectation value of this operator is expected to be a function of time. And how is it defined? It's defined by doing the following integral. Again, from minus infinity to infinity, dx psi star of x and t, and then the operator a acting on psi of x and t. And psi is supposed to be a normalized state. So notice the notation here. We put the psi here because the expectation value, whenever somebody asks you the expectation value of an operator, it has to be on a given state. So you put the state. Then you realize that this is a time-dependent wave function, typically, so it could depend on time. Now, we said about stationary states that if a state is stationary, there's a single time exponential here. There's just one term, e to the minus I e t over h bar. And if a, of course, is time-independent operator, you won't care about the exponential, and it will cancel this one, and there will not be a time dependence there. But if this state is not stationary, like most states are not stationary. So remember, it's very important, if you have a stationary state and you superpose another stationary state, the result is not stationary. Stationary is a single exponential. More than one exponential is not stationary. So when you have this, you could have time dependence. So that's why we wrote it. Whenever you have a state that is not stationary, there is time dependence. Now, you could do the following thing. So here is a simple but important calculation that should be done. And it's the expectation value of h. So what is the expectation value of the Hamiltonian at time t on this wave function psi that we've computed there? So we would have to do that whole integral. And in fact, I ask you that you do it. It's not too hard. In fact, I would say it's relatively simple. And you have h on psi of x and t. And then you must substitute this psi equal the sum of bn's psi n's. And you have two sums. And the h acting on each psi n, you know what it is. And then the two sums, you can do the integral using orthonormality. It's a relatively standard calculation. You should be able to do it. If you find it hard, you will see it, of course, in the notes. But it's the kind of thing that I want you to review. So what is the answer here? It's a famous answer. It's bn squared en. So you get the expected value of the energy. It weighs, it's a weighted average over all the stationary states that are involved in the state that you've been building. So your state has a little bit of psi 0, psi 1, psi 2, psi 3, and for each one you square its component and multiply by En. And this is time independent. And you say, well, you told me that only for stationary states things are time independent. Yes, only for stationary states All operators are time independent, but the Hamiltonian is a very special operator. It's the energy operator, and this is a time-independent system. It's not being driven by something, so you would expect the energy to be conserved, and this is pretty much the statement of conservation of energy, the time independence of this thing. My last remark is technical about normalizations, and it's something you may find useful if you have a wave function that is psi, which is not normalized. You may say, okay, let's normalize it. So what is the normalized wave function? The normalized wave function is psi divided by the square root of the integral of psi star psi dx. You see, this is a number, and you take the square root of it. And this is psi of x and t. If psi is not normalized, this thing is normalized. So think of doing this here. Suppose you're kind of don't want to work too hard, and you don't want to normalize your wave function. So your psi is not normalized. Well, then this is definitely normalized. You should check that. Square it and integrate it, and you'll see you'll get 1. But then I can then calculate the expectation value of A on that state, and wherever I see a psi that should be normalized, I put this whole thing. So what do I end up with? I end up with this integral from infinity to infinity, dx psi star a hat psi divided by the integral from minus infinity to infinity of psi star psi dx. So if you don't want to normalize a wave function, that's okay. You can still calculate its expectation value by working with a not normalized wave function. So in this definition, psi is not normalized, but you still get the right value. Okay, so that's it for today. Next time we'll do properties of the spectrum in one dimension and begin something new called the variational problem. All right. Thank you. Thank you.